Alright, so yesterday we were investigating this graphical characteristic of end behavior. Like as we travel to the left and as we travel to the right on a graph, does it rise or fall, meaning go up and down? And we were looking at that connection between the end behavior and how the equation of a polynomial looks, okay, with its relationship with the degree, whether if it's even or odd, or the leading coefficient, that number out front, okay, is it positive or negative? So if you need to take a second and take a look at what we did yesterday with the like the four relationships we discussed, we had a little chart. I think that was on page 158 maybe. We're going to reference that chart today a little bit to help us through some of these more examples. So we're going to take a look at another table example like we left off yesterday with, but then we're going to get into the good ones where we're finally going to graph polynomials by hand. Based off of all these characteristics and properties that we've been identifying, maybe we can use those to our advantage to help us get a picture of a polynomial without a calculator. Okay, so we'll get there later today. So very similar to the one we did yesterday, we have a table of values. They tell us it's a polynomial, so we have like this roller coaster type shape. The zeros are the only ones in the function, so there aren't any hidden ones in there that we need to worry about that we don't know. And the multiplicities are not greater than 2. Okay, so there's no multiplicities of 3 going on. Based off of that information, we're going to try to pick apart some of the characteristics of this polynomial. So let's first start off with the left and right end behavior. Okay, if you were to graph some of these points and maybe connect them to make a roller coaster type shape, what would the left side of the graph be doing? What would the right side be doing? Can you tell? Yeah. How do you know?
Because if you look at -6, it's 360 for the y, so it'd be rising.
Yep.
And then if you look at the 4,
Mm-hmm.
and then the 4, 9, it determines that it's rising as well.
They're rising as well. Those are very, very large ending values that we have on the table. So we're just going to assume at that spot or at those locations, the graph is just going to continue to go up. Okay, so rising on both sides, we have very positive values. All right. Based off of that end behavior, okay, rising on both sides, what can we determine about the degree? Okay, is it even or odd? And then what do we know about the sign of that number out front? Is it a positive number, negative number? What do you think? How do you know it's even? All right, so one of the characteristics or kind of relationships we saw yesterday from the table, if the left and right are the same behavior, we have some type of even function. So, or even, not function, even degree. All right, even because the end behaviors are the same. Okay, even degree. And Marie, you said positive as well, is that right?
Yes.
How do you know it's positive? Positive leading coefficient. Positive number. Not necessarily that they're both rising. Which one do we look for the what? Say it again? The right-hand side, because the right side rises. Good. All right, so far so good. Let's go ahead and look at the table a little bit further. Can we identify those x-intercepts? Where are we located on the x-axis based off the table? What do you think, Brianna? How'd you know?
They all have y values of 0.
All right, because y values are 0. All right, so based off of those x-intercepts, maybe we can look at the table a little further to determine their multiplicities. What does the graph look like at those spots? So we'll label those as well. What do you think the multiplicity of the -3 x-intercept is? Yeah. How do you know?
Because the before and after
They're both, there's no sign change. Good. So you're above the x-axis on the left and the right. Okay, so you're just bouncing or touching the x-axis at that spot. So justify your answers. We'll say no sign change. What about the multiplicity of the negative 1x intercept? Yeah. How do you know it's 3? Alright, so there is a sign change, which means you do go through the x-axis, so that it could be a 3 or a 1, because those are the two that go through. How do you know for sure it's a 3 though? Yeah. There are no zeros. So if it can't be greater than 2, it would have to be the 1 then. Okay, so this would have to be a multiplicity of 1. We'll say, because there was a sign change, what about the multiplicity of 2? Yeah, Marie? 1 as well, because we have that sign change. Good. So we'll give the same reasoning. So I want you to add in part D, kind of like we did yesterday. We're going to bring all of this information and all these properties together to help us write the equation. Okay, not a possible equation, like the exact equation that would give us all of those data points from the table. Okay, so let's go ahead and start off with the general one. Okay, and then we'll fill in some missing information to help us be a little bit more specific. So can we first fill out, let's see, they name this g of x. Can we fill out what some of the equation might look like based off of what we've identified so far? Yeah. Uh-huh. Okay. X minus 2. Okay, so the a out front is signifying that coefficient, okay, some number out front, and we said it has to be positive. The factors are coming from your zeros. Remember, we kind of need the opposite number in there. And then the powers on the factors are coming from those multiplicities. So we have a 2, a 1, and a 1. So right here, this is a general equation that would represent this table, but we should be a little bit more specific because we do have many more data points that we could possibly use to our advantage to help us figure out what is that number out front. Okay, what specifically is that leading coefficient? So can we think about how we did that yesterday? How can we take this a step further? Yeah. Pick any point you want. Okay, so taking a look at some of the numbers, a lot of them are decimals. Maybe we'll pick some whole numbers. You could do the -6 and 360. You could do the 4 and 490. You cannot use the x-intercepts though, okay, because we already used that information to help us with the factors. Okay, so that's kind of a key point. If you tried to use one of those, it wouldn't work out because you already utilized them. All right, so which one do we feel like using? Do we want to use the -6, 360? Yeah. You want to use the 4? That's fine. Okay, so we'll go ahead and plug in 4 for all the x's, and then the 490 in for y. Alright, so 4 plus 3 is 7. 7 squared, we got 49. 4 plus 1 is 5. 4 minus 2 is 2. Anybody have a calculator handy? Yeah. Say it again. Does it really? If you multiply all those together, it's 490? So then our a value is 1. That's kind of weird. Wasn't yesterday's a value 1 as well? It might not always be that. Okay, let's not get used to that or think that it's always going to be 1. Okay, so let's go ahead and substitute that a value in for the general A that we had before. So the equation that would generate this table, we would have 1 times x plus 3 squared times x plus 1 times x minus 2. Yeah. Yeah, if you don't want to write the 1 there, you don't have to. Yeah, that's okay. All right, how did we do? Did we lose it from yesterday? I hope not. We're good? All right, perfect. So let's go ahead and we're going to step it up a bit. We're going to graph some polynomials by hand, okay? No calculator necessary. We're going to utilize some algebra techniques, some graphical characteristics to help us complete these. So I do kind of give you some guiding ideas to think about, some guiding steps in this paragraph at the top. What we're going to try to do is factor our polynomial if it's not already factored. Why do you think that would be beneficial? What do the factors tell us about the graph? Yeah. It tells you where the x-intercepts are. Okay, so maybe that's something that we can identify. So notice how this is not factored. Okay, this is in standard form. We're going to try to factor it to get those little parenthesis groups. So if you think about your factoring techniques, what do you want to try first on this polynomial? Yeah. All right, let's take out a GCF. Can we factor further? You want to keep going? Yeah. Two numbers that multiply to 4 but also add to 4. Notice how this kind of fits that I am profile, okay, because your coefficient is 1. So two numbers that multiply to 4 but add to 4 would be a 2 and a 2. Okay. Do you notice how the x plus 2 factor shows up twice? Okay, so if you wanted to, you could rewrite it as x plus 2 squared. Okay, but you don't necessarily have to do that if you don't want to. Alright, so if this is how it factors, maybe we can identify where the x-intercepts are located, but also what their multiplicities are. Okay, what does the graph, or what's the graph going to look like at those spots? So maybe we'll make a little chart, z for 0 and then m for multiplicity. Where are some of the x-intercepts? What do you think, Hannah? -2, okay, so that would come from this x, and what's the multiplicity of that 0? 2, right? That was how many times the factor showed up. Do we have another x-intercept somewhere? Yeah. 0, and how many times does that show up? Once, right? The power on that x is 1. Alright, so let's go ahead and graph these. So we know we can put a dot at -2 and a dot at 0. Alright, based off the multiplicities, we know we're just touching the x-axis at -2 and we go through or strike through the x-axis at 0. But the issue is, okay, if I'm just touching the x-axis here, how do I know which direction I'm just touching it on? Do you see how we kind of need to clarify which one? What do you think? Yeah.
Well, the leading coefficient is negative, so the behavior would be going well, since it has, well, two things. You can determine by the degree itself that it has opposite end behavior.
Perfect. Okay, so we're going to utilize the end behavior that we've been talking about from yesterday to help us determine exactly which way this graph is going. So where were you looking, Rebecca, to help you with that?
Well, the leading coefficient is negative.
Okay.
So that means that it would have to be, the end behavior on the left would have to be pointing up, and the end behavior on the right would have to be pointing down.
Perfect. Okay, so since the leading coefficient's negative, we automatically know the right side is going down. So what I would do personally to kind of denote that idea is on the right side of your graph, I would draw an arrow going down. Now to figure out what the left-hand side is doing, Rebecca noticed how the degree, okay, the highest power is 3, which is odd, so the end behaviors should be opposite. If we're going down on the right-hand side, then that means we should be going up on the left. So I'm going to draw another little guiding arrow going up on the left-hand side. So what we need to do is kind of play connect the dots, if you will, or connect the arrows. We're going to draw a graph. Remember, you read a book from left to right, so we're going to draw a graph the same way. We're going to start with this arrow, and we're going to connect it to the first x-intercept that we identified. All right. Now we set it this x-intercept, since it had a multiplicity of 2, that it should just be bouncing. So we're not going to go through the x-axis there. We have to bounce back up. We're not quite sure how high it goes. Okay, this is just a rough graph that we're drawing. But we do know that we have to connect it to this other x-intercept that we know is already on the graph. So we're going to kind of have a little hump in the middle there. This x-intercept, though, had a multiplicity of 1, so we know we need to go straight through. Okay. And if you want to connect it with this arrow that you drew on the bottom right-hand side, you can. Maybe something like that. Maybe some of you want to make it a little steeper. Okay, we just need some arrow on the right-hand side going down. There's many different graphs or shapes that you can have. But we need to be going up on the left, down on the right. We have these x-intercepts, and we're making sure that the multiplicities look appropriate on the graph. Okay, so it's just a generic graph, but at least it's some type of shape that we can produce. How was your first graph? Graphed it by hand. No calculator needed. Okay? If you wanted to check your work, you could type this in. Okay, I bet it would look something like this. But it could be, depending on the window you use, it might be a little distorted. All right, let's go ahead and try the next one. So we're going to factor it first, trying to find those x-intercepts. Think about your factoring techniques. What do you want to try for this one? Yeah. Grouping. We got 4 terms. All right. So GCF for the first group. Yeah. X squared. So we're left with the 2x plus 3. And then GCF for the second group, so that we're left with another 2x plus 3. Yeah? Say it again. -9. Alright, so our 2 factors, we'd have x squared minus 9 and a 2x plus 3. What do you want to do, Marie? We can keep going. Alright, so even though we're done with grouping, we can still use another technique. We have a difference of perfect squares. So we need an x plus 3 and an x minus 3. Looks good. So based off those factors, let's go ahead and identify the zeros, okay, x-intercepts, and their multiplicities. Yeah. -3, okay, and its multiplicity? 1, yep. Any other ones? Yeah. +3 and its multiplicity? 1 as well, good. Yeah. -3 halves, that's the same as -1.5, and its multiplicity? 1, good. Alright, so let's go ahead and plot those on the graph. We have -3, +3, and -1.5. Alright, we know that we're striking through these points because they're all multiplicities of 1. But the question is, do we strike through this way? Do we strike through that way? Okay, we need some type of guiding arrows to help us determine which strike we have. So this is when we're going to utilize the end behavior, okay, to give us those directions. So take a look at your degree, take a look at your leading coefficient. What's that signifying? What do we know? Yeah.
It's positive, so the right side would rise and the left side would fall.
There we go. All right, positive leading coefficient, so the right side goes up. And since the degree is odd, we know the end behaviors should be opposites, so the left side should go down. All right, so kind of playing connect the arrows, connect the dots, going left to right. We're going to connect the first arrow to the first x-intercept, and we know we need to go straight through that. But we do need to come back down to connect it to the next x-intercept. So we're going to have a little hump. We need to strike through that x-intercept as well, and then connect it to the next one. And we need to strike through that one as well based off the multiplicities. So you can connect it to your arrow. If you want to make it more drastic and go straight up, you can. Okay, as long as you have an arrow going up on the right-hand side, you're fine. How are we doing on the second graph? Pretty good? Old school calculator. We're using our brain. All right, let's check out some more. These look a little different. What's different about these equations than the two that we just did? Yeah. They're already factored for us. Okay, so this is nice because it's kind of skipping a step for us, but we may have to analyze these equations slightly different. So we'll see how these kind of work out for us. If this is already factored, we should be really easily able to figure out the zeros and the multiplicities. What do you think? Good, Marie? -2, 1, and 3, and their multiplicities? All ones. Good. Okay, we have powers of ones. So let's go ahead and graph those. -2, 1, and 3. But now we need those guiding arrows in there to help us determine how we specifically strike through the x-axis at these spots. So what we need to determine is what is the degree and what is that leading coefficient. Is it positive or negative? Now this is what's a little tricky, because if you take a look at the ones we just did, okay, I'm going to put them up here on the screen. It was really easy for us to look at the end behavior when the equation's in standard form, because all we have to do is look for that largest power and that number in front. Okay, but in factored form, okay, we don't know what the largest power might be, at least at first glance, and we're not quite sure what the leading number is at first glance. So we have a little bit of figuring out to do here. Okay, in your head, if you were to think about multiplying all of those together, okay, like getting rid of all those parentheses, what would the highest power be? Can you think about it? Yeah. How'd you know it's x to the third? Yeah. Exactly. We have an x to the first times another x to the first times another x to the first. Okay, and we're just looking at the x's. We're looking for the highest power attached to one of those variables. So x to the first times another x to the first times another x to the first would give us an x to the third. So this is what your degree and leading coefficient would look like, okay, all together in one term. So based off of this, notice how the degree is odd and the leading coefficient of 1 is positive. All right, so positive leading coefficient, we know we're going up on the right. Odd degree means we have opposite end behaviors. So we're going down on the left. And we're going to play connect the dots and arrows to form our graph, making sure that we strike through the x-axis at these spots. So maybe something like that. Okay, if you want the ends of your graph to be a little bit more kind of steep, you can do that. But you just need some general shape going down on the left, up on the right, striking through those x-intercepts at the right spots. All right, so in factored form, it's kind of a not a double-edged sword in some ways. It's really easy for you to figure out the zeros because you don't have to worry about factoring it, but you do have to do a little figuring to help you determine that first term. Okay, what's the degree and what's the leading coefficient? All right, so let's try the next one. Maybe we can identify zeros and multiplicities. What do you think? Yeah. Negative 1 and 2 and their multiplicities? There we go. Okay, so we'll plot those on the graph. Negative 1 and 2. So we know we should be bouncing at negative 1, but we strike through at 2. All right, let's get those arrows in there to guide us. If we look at the first factor, we're going to have an x squared times an x to the first from the second factor. Okay, if we were to multiply all these together, x squared times x would give us an x to the third. So let's analyze degree and coefficient. Positive leading coefficient, we go up on the right. Odd degree is opposite end behavior, so we should be going down on the left. All right, so playing connect the dots. We're going to connect the arrow to the first x-intercept. We should be bouncing at this spot. So we're going to go back down and then connect it to the next one so we have a little hump. But at 2, since the multiplicity is 1, we're going to go straight through it. So we're going to continue up from there. We're doing okay? So far so good? All right, let's take a look at one that's slightly different. All right, h of x is already factored for us, so zeros should be pretty simple to find. What do you think? Yeah. Negative 2 and 2 and their multiplicities? Both 2. Alright, so we're bouncing at both spots. Alright, so now we got to think about if we were to multiply all of these together, what would we get? Okay, as that highest degree and that leading coefficient. Now here's what's a little tricky. Do we see that negative sign out front? Okay, we're technically multiplying that as well, right? A negative times some quantity. So let's not forget that negative out front. We then have an x squared, eventually times another x squared. So a negative times an x squared times another x squared would be a negative x to the fourth. All right, so let's take a look at that to help us determine the arrows. Okay. We have a negative leading coefficient this time, so the right-hand side goes down. What about the left-hand side? Yeah? How do you know? Yeah. They go in the same direction, right? We have an even power, all right? So they're doing the same end behavior. So playing connect the dots and arrows. When we get to the first x-intercept, we have to bounce, multiplicity of 2. So we're kind of going to create another hump because we need to eventually connect it to the next x-intercept at 2. But we should be bouncing there as well, which means we can connect it to the last end behavior arrow that we drew. So we kind of get this M type shape. We doing okay? Do you guys think you can try one on your own? Maybe try the next one. Try K of X. See how you do. How did we do? Check it out. Pretty close? Alright. This is the first time we had a multiplicity of 3 show up. So at your x-intercept of 1, you really need to show how it's level there. Okay, not striking through like some of the other ones we had. So if you want to exaggerate it to make sure that it's clear, might not be a bad idea. Okay, but multiplicity of 3, we need to be level. Anything we want to go over from that one? So far so good? Alright, let's check out the next one. Let's see, already factored, so zeros and multiplicities should be easy. We have -1. Ooh, another -1, right? So we're not going to write it twice, okay? But what would the multiplicity be if it shows up twice? Wouldn't it be 2? Okay, because technically you could write this as x plus 1 squared, because you have two of them there, right? So 0 of -1 shows up twice, and then we would have 3 as another 0, and that just shows up once. So we'll go ahead and plot those. Okay. Let's go ahead and take a look at the end behavior. So from the first factor, we have an x squared. And from the second factor, this one's a little different too. Notice how typically the x is written first, right? But in this one it's written second. And in this case, the x is negative because you have a subtraction sign before it. So this is technically a negative x to the first. A little different for that one. So if you were to multiply those together, we'd get a negative x to the third.
Excuse me, interruption. At this time, I need teachers to send students with your toys to the front lobby to load them into the truck. The Army truck couldn't make it because of a technical difficulty, but we have a big pickup and they're still going to deliver them to our Freeport Food Bank. Thank you to everyone who participated. Please send all the toys up now. Thank you.
Do I have a volunteer who wants to go? You want to go, Marie? Our box is over there, okay? All right, so end behavior looks like leading coefficient's negative, so right-hand side goes down. Odd degree, so opposite end behaviors, which means the left-hand side goes up. And let's play connect the arrows and dots. So we're going to reach -1. Multiplicity of 2, we should be bouncing. Bless you. So we have a little hump. And then when we connect it to 3, we need to strike through the x-axis at that spot. So we'll connect it to the next arrow. Alright, that one was a little tricky because the x happened to be negative. It was being subtracted in the factor. So it can be a little difficult to pick that up when you calculate your leading coefficient and your degree. Can you guys try the last one? We'll end with a bang. Alright, let's check out the zeros. So -3 from the first factor and +3 from the last factor are kind of obvious. The 0 from the middle one's a little difficult to think about, but if you were to set that equal to 0 and solve for x, you would eventually get 3/2, aka 1.5. Okay, so if it's a little difficult to figure out, just set it equal to 0 and just solve for x from there. Based off the powers, you have your multiplicities. So we can plot the x-intercepts and at least know graphically what's going on at those spots. But we need those arrows that come from the degree and the coefficient to help us out. So from the first factor, we have an x to the first. From the second factor, we have a -2x to the first. And the last one, we have an x squared. So multiplying all those together, we would eventually have this as our first term in standard form. So even degree, we have the same end behavior, and since the leading coefficient's negative, we know they're both going to be going down. So playing connect the arrows and the dots, we can get that rough shape. How'd you do? Pretty good? Question? Yeah.
Instead of finding the first term, I just do multiplying, but not multiplying, just adding the multiplicities, so it's less clear.
You could do that. Okay, so notice how, didn't we say before one of the connections was adding the multiplicities and that would give you the degree? All right, so 1 plus 1 plus 2, that would give you 4. Okay, what's a little trickier to figure out though perhaps is the leading coefficient out front. So did you have a certain way to determine that?
Well, I just, by looking at it, like,
Mhm.
just looking at the factors, I could tell, like, if I had to factor out a negative
Mhm.
x, I could tell.
You could tell. Okay, so for you, if you can tell, that's fine. Some people might not be able to see that connection as clearly, so that's why I think this might be a little bit more procedural for them. But if you have your own way that can generate the same results, that's perfectly fine. Okay? We're doing okay? Hanging in there? Not gonna lie, guys, this is pretty like high-end, difficult stuff. So if you're feeling good with that, that's awesome. Not too hot, not too cold, not too fast, not too slow. Feel like Goldilocks. Perfect. All right, so tomorrow we're going to have a free response day. We're going to take a look at some questions. Next week on Monday we'll have your review day and then unit test Tuesday, Wednesday. Deal?